Good afternoon, everyone. Well, thank you for sticking around until late into the event. I'm very happy to give the last talk in the last session, which is, I'm going to try to drive home the key theme of this conference, which is open source to honor the spirit of PyTorch, and also superintelligence, which is to honor the theme of the age. So under the big banner of superintelligence, we've seen a lot of progress these days. They are now deployed as a very, very exciting and useful apps in the space of chatbots, image and video generations, and even in AI for science. But there is something that is a little bit discomforting. Most of the frontier results these days are from preparatory implementations enabled by the big tech companies. And they are the front runners in both performance and also in adoption, and also in many other commercial opportunities. There is another pillar of source called so-called open source, but actually means open weights, pioneered by models like Lemma. But these days are really spearheaded by many Chinese companies, such as the DeepSeek projects, the Kimis, and so forth. If you look at the open source community, there hasn't been yet a very competitive initiative that's matching the performance and also the popularity of those big large language models or intelligent models. There are some examples from AI tool, but the performance is not good enough. So what I'm going to talk about today is an effort that we've been working on in the past few years in setting up a new program called the Institute of Foundation Models, which is to try developing and carry out research on industrial scale, high performance large language models, and maybe more foundation models, but in a style that is more compatible, more open, as we academics do. And I'm going to tell you a little bit about one of the models called K2. So this is FM. It was established just a few months ago right here in Silicon Valley, but it also has the lab in Paris and in Abu Dhabi. And they actually were founded by veterans who were in the space in a scattered fashion. For example, they were builders of the first open source chatbot, Vicuna. There are developers who made possible the chatbot Arena, and so on and so forth. So now we converge into this program in order to develop a series of foundation models to rival in terms of performance and maybe in terms of innovation against some of the big players in the space. And we want to use this program to help redefine some of the slightly abused concepts. For example, openness. What do we mean by openness? Here, I want to emphasize openness really means no dead angle, 360 openness in terms of open source repository, such as sharing not just the weights of the models, but also the code, the data, the checkpoints, and maybe the training recipes and all the secret sources, so that just like what you do in publishing academic papers through peer review, you want people to reproduce the results. So this is what we do in the LLM 360 project. We also want to redefine performance as a small institution with limited resource. For example, this is a plot showing you the performance of a deep reasoning model called K2 Think we released, actually launched about a month ago. It is a model of 32 billion parameters focusing on advanced reasoning in math, in coding, and in science. And you can see from this plot, the performance is actually on par with those open source models, open weight models that are 20 times bigger, and some of the closed source proprietary models which are 100 times bigger. Right? So we're trying to now punch above its weight using technical ideas that is often only possible in the academic community by a lot of experimentations and explorations without the pressure of quick and fast commercial-driven release. And this is some report of the reception of this model. We are still very small. We haven't promoted it heavily, but so far we've seen some good trends in studying and in using and in adopting these models. In fact, right now there is a hackathon going on in Abu Dhabi where tens of thousands of developers on the world are gathering to develop applications on top of it. And there are use cases where people told me that they are using the K2 model to do open space mathematical derivations of their biophysics and other mathematical problems, which is kind of interesting. And also there are a lot of other user experience feedbacks, such as speed. By the way, speed is one of the other signature of K2 Think. It is now running at 2,000 tokens per second, roughly 10 times the speed of otherwise equally performant models. And we were able to implement a wide range of recipes of new ideas, such as what I listed here: supervised fine-tuning, reinforcement learning with verifiable rewards, agentic planning before you do the reasoning, and test time optimization and scaling, and so on and so forth. It is really a showcase where good ideas and clever implementation can actually overcome your deficiency and the disadvantage in terms of resource and the parameter size. And we are actually continuing this trend. A few larger base models with the reasoning capability built in are being developed. And in the next couple of months, we'll be releasing a few new models with both dense and MOE architecture. And even from the curve you see here, they seem to be very promising by showing a rather dominant and impressive performance over many of the standard reference models out there. Now, the topic is also about the superintelligence. Is LM alone is going to lead us to there? Well, wait a second, right? And we know that LM are good at many things, such as deep math, but they also have some difficulties in solving even simpler questions. This is an example. I actually tried this picture just a few days ago with GPT-5 to answer this very simple question. I'm sure that you all know the answer. And here is just a snapshot about the answer I got from there, which is kind of funny. And if you trigger the GPT-5 Think, which will take longer and do deeper reasoning, you get a slightly less certain wrong answer. You actually could try deep research and try half an hour, the answer can still be wrong, right? So that means you need something beyond LM to achieve what we call superintelligence. And here are some more examples which actually show that LM really have some limitations in understanding our very universe that we live in. I think the reason is very obvious, because all these LMs are doing their reasoning using text tokens and in the space defined by our textual literature, right? If you want to go into the open space in the physical world, like this, walk into a picture as a gamer, or send your bot into the real world, you have to have a way to perform reasoning in real physical world. And that means you need to have a bigger space of data and information to train the model. If you want to even do further and add some agents into the universe like this, then obviously the answer is to enlarge further the space of a problem and data and inference to include multi-agency capabilities. And then you can just follow this thread and go even further, say how to do biology correctly, with LM like very deep reasoning. Well, again, you enlarge space to include more data and coming up with maybe a more powerful model able to ingest this data. Right. So I'm going to spend a few words to talk about some of these efforts taking place in FM. And also I'm going to take the chance to clarify some of the misconceptions, because word models, agent models, bio models has been now a table stake keywords everybody is talking about. Not necessarily punching or hitting the point. For example, what is a word model? Under the name of word models, we saw already a good collection of great apps which more or less do the same thing to provide you images and videos, and maybe impersonate yourself into those very, very interesting video themes. But I don't think this is getting the point of why we do word models, why we human beings have a mental world. We use the mental world to do reasoning, to do deep reasoning. And sometimes we even use the mental world to learn. For example, how do you learn chess? You use your own mental world of the chessboard or the Go board to do self-playing and learn, right? And these are not yet highlighted as the main goal of word models. So here I want to re-emphasize our definition of the word model to be a simulator of all possibilities that you want to reason about, which includes, of course, the physical possibilities in real world, but also embodied experiences, even emotional experiences, social experiences, and maybe even counterfactual experiences that never happen in real world. Because by simulating them, you can go do experiments without experiencing those kind of risk. And along the way, we are actually building these models using a new architecture called the Generative Latent Predictive Model or architecture. By the way, this is not a JAPA architecture. If you are interested in the mathematical difference of this model versus JAPA, you can go read one of the papers I recently published. So to summarize the differences, this generative latent prediction model is trained by reconstructing data. And JAPA is trained by reconstructing latent representations. So reconstructing data is very hard, but it is algorithmic difficulty. But reconstructing the latent representation is mathematically incoherent because there is a mathematical flaw in terms of collapsing and identifiability. So in here, the model builds on the previous success of language model, using language models and diffusion models as the backbone for long-range and short-term and short-range inferences, and having a diffusion and the encoding-decoding structure to generate simulations and the realities, like what you're seeing here. All sorts of different realities can be generated in a stable fashion so that you can continue to do reasoning inside that. So this is the word model we're going to release in an open source fashion in the next couple of months. Well, we just heard about talks about agent models, but recently you must have heard about Andrew Karpathy's comment about agent models, right? They're not very smart. And they don't learn so quickly, or maybe at all, when doing the job. And sometimes they forget. I think the agent model needs to also be reinvented with a new architecture which at least supports the following functions, such as learning from experiences, adapting to environments, and also generalizing across different tasks. And we also are working on that. This is the architecture built on the word model I just represented, where you have an architecture allowing two types of inferences. One is the system-wide inferences in a supervised fashion. From policy, you can quickly react to a reasoning task. But the second one, which is what people are very, very good at doing, is the system 2 reasoning, which is slow, deliberate, and conscious, but very goal-driven, using simulative reasoning supported by the word model to simulate different scenarios. Actually, this is what the agent would look like inside such a word model supported agent models. This agent actually are treating the objects and the content he encounters as other agents. Therefore, there are connections beyond just object-level interactions, but also mindset interactions and the intention interactions. Therefore, he could figure out the strategy to escape a dangerous scenario very, very smartly and strategically. Now, last but not least, we also are working on AI for science. One of the problems in science, such as biology, is that the data is inadequate. And also data is very complex. For example, in biology, there are data of a sequence form, of structure form, network form, graph form, image form, and so forth. And the current practice in the AI for science domain is to borrow a LLM, replace the data with the biological data or whatever other data they have without changing the architecture a lot, or maybe at all, and then try to reason about the outcome in an LLM fashion. So this is not what we do. We are trying to utilize the resource and the experience we gained from word models and agent models to build a multimodal and multi-scale foundation model You've heard about the virtual cell. That's actually part of the vision. It's called the AI-driven digital organism, which is to integrate all this information holistically so that you can simulate a biological phenomenon from bottom to up in the whole organism level. So what could be use case? For example, in the old-fashioned drug design process, you need to go through all these sifting processes to select and filter out one successful design out of many, many possibilities. But with a ADO model, like a biological simulator, you could pretty much simulate not only the design, but also the environment the design is going to work with, and then come up with a safe design before you even deploy or experiment with wet labs. So that's how we see the future of AI-driven natural science is going. You simulate first, and then you treat reality as verifications. But again, going back to our home message, doing science needs to be open because we need a community to together study the problem together, which now is becoming difficult because of not only the resource issue, but also this culture issue, that people do not necessarily publish everything that they have. At most, you see some weights of the models, but it is not enough for you to reproduce and also to innovate on top of it. So what we are calling for is to adopt such a more aggressive open source strategy where the data handling, the optimization setting, the learning schedules, the technical treatment of your infrastructures and the fine-tuning and other things, maybe even the validational benchmarks should be kept open and accessible to all. And that's basically what our institute, Institute Foundation model is trying to promote and also to carry out. So I want to end by inviting all of you to play with our models and even contributing to our platform and together build a bigger and more vibrant open source community toward artificial superintelligence. Thank you very much.